Hi friends, this video is on measurement of the renal blood flow or measurement of the renal plasma flow and what is the basis for using para-aminohippuric acid PAH to measure the renal plasma flow and renal blood flow. At the outset, let me say I'm going to use the terms interchangeably, renal plasma flow and renal blood flow, because obviously blood, 55% of it is the plasma, and therefore when we measure one, the other one is running parallel. So the point being that with para-aminohippuric acid injected into the plasma, we measure the renal plasma flow, and from that we calculate the renal blood flow. How do we do that? Let's figure out. Okay, now the first thing, why do we have to measure the renal blood flow? Well, there are certain conditions, for example renal artery stenosis, or maybe certain ligands locally acting or systemically acting which may alter the renal blood flow and thereby disturb the GFR and many other parameters, and for these reasons we need to measure the renal blood flow. What are the methods? Well, there are technologically advances, and therefore now it's easier by the methods such as color Doppler or use of such instruments. But conventionally, traditionally, para-aminohippuric acid has been used to measure the renal plasma flow and renal blood flow. So this video is all about why do we measure, why do we take PAH, why it is convenient and suitable to use PAH to measure the renal plasma flow and blood flow. All right, so let's start. Now the first point is measurement of the cardiac output is by the Fick principle, direct Fick method. Cardiac output is equal to oxygen consumption by the entire body upon arteriovenous oxygen difference for the entire body. Cardiac output is the blood flow which is flowing through the entire body, and therefore that's the Fick's principle for the cardiac output. Same principle can be used to measure the blood flow to a particular organ. After all, what is cardiac output? The sum of blood flow to all organs is equal to cardiac output. So same principle can be used or applied for measurement of blood flow to a particular organ. Now let's say we are measuring blood flow to a particular organ. The principle becomes oxygen consumption by that particular organ upon arteriovenous oxygen difference in that particular organ. That's how we can apply the Fick's principle for measurement of blood flow to a particular organ. Here we are talking about kidney, renal blood flow, and therefore the same principle we will apply, but this time we will not use oxygen, we will use a substance X. That substance X may be injected, and then the renal blood flow is equal to, instead of oxygen consumption in the numerator, we have consumption of X by the kidney upon arteriovenous difference of X in the kidney. Instead of, in the place of oxygen, we are taking X, substance X, and therefore arteriovenous difference of X in the kidney, which I have written as renal artery concentration of X minus renal venous concentration of X. So that's arteriovenous difference of X in the kidney. This will give us the renal blood flow, all right, with the application of Fick's principle. But this is very tedious, very difficult to access renal artery, to access renal vein, collect the samples, measure the concentration of X. That's easier said than done. Can we not have something, some method whereby we just have a substance X, we measure its plasma concentration, we measure its urinary concentration or urinary excretion rate, and that's it, it gives us the renal blood flow? Can it be that simple? Yes, it can be that simple with the use of PAH and let's find out why. Why is it like that? Why it's so easy with the use of PAH? Right now I have also written the clearance equation for a particular substance X. Clearance is equal to UV upon P. That is, denominator has plasma concentration of the substance and numerator has UX into V, urinary concentration of that substance into total volume of urine, that is total excretion rate of a substance. That is in the numerator, and this relationship is called as the clearance for a particular substance. Now, coming back to our original Fick's equation, we have renal blood flow measured by these three things first to be measured. So, we are looking at such a substance X which has to have three properties. Let's go one by one. Now, in the numerator, consumption of X by the kidney per unit time maybe. Now, we need such a substance X which is consumed by the kidney, fine, but not by metabolism or inactivation or any such thing. Kidney should consume that substance X, means it should eliminate that substance X into the urine. In that case, consumption of X by the kidney will be same as its urinary excretion rate. So numerator in the Fick's equation, consumption of X by the kidney will now become urinary excretion rate of that substance, because the kidney consumes X, and consumes means what? Does not metabolize, does not handle it in any other way, simply excretes that substance into the urine. So consumption of X by the kidney will be same as its urinary excretion rate, and that we already know how to calculate urinary excretion rate of a particular substance. It is UX into V, total excretion rate of a substance into the urine. So this substance is consumed by the kidney, and that is, it is eliminated into the urine, excreted into the urine. That's the numerator. Second, if this substance X, look, denominator is renal artery concentration of X and renal venous concentration of X. We don't want to go to renal artery, we don't want to go to renal vein to collect the samples and measure the concentrations. Instead, if this substance X, the second criteria, if this substance X is not handled by any other organ except kidney, only kidney handles this substance and excretes it into the urine, no other organ in the body handles the substance X. Which means what? Which means renal artery concentration of that substance will be same as its systemic plasma concentration. The substance X is present in the systemic plasma, and all of it as such comes into the renal artery, because no other organ in the body is handling this substance X. So its concentration is not changing at all. Whatever is there in the renal, whatever is there in the systemic plasma, all of it is coming into the renal artery. So in that case, we don't have to go to the renal artery to measure the concentration of X. Simply, renal artery concentration of X will be same as its systemic artery concentration, systemic plasma concentration. So now denominator, we have renal artery concentration in the Fick's equation, but the problem solved. We don't have to go to renal artery to collect the sample. We just have to collect the plasma concentration of that substance. We just have to collect the plasma sample. So in the place of renal artery concentration, I write plasma concentration of that substance. And the third criteria, as I said just now, we don't want to go to renal vein. In the Fick's equation, we will need venous concentration of that renal venous concentration of that substance, and we don't want to go to renal vein to collect the sample. It's very difficult to access the renal vein. So the third criteria is, what if the substance is completely removed by the kidney in a single pass? The substance X is completely removed by the kidney, and removed by the kidney means excreted into the urine in a single pass. Let's discuss this particular criteria or this particular property. There are substances in the plasma. They come into the kidney, they enter the kidney. Kidney handles them in a certain way, like 20% will be filtered, some of the substance might be even secreted, but all the substance, entire amount which was present in the plasma does not get excreted into the urine. I'm talking about the other substances, or any of them, like sodium, glucose, potassium, chloride, calcium, or amino acids, any of them. They are there in the plasma, they come into the kidney, certain fraction is excreted into the urine, and the remaining part of the remaining amount goes back in the renal vein. It goes back into the body, circulates, and then comes back again. This particular substance X, it is completely removed by the kidney in a single pass. That means from the plasma, from the systemic circulation, when it enters the renal blood, then by filtration and by tubular secretion, 100%, all of it is excreted into the urine. Which means what? Which means it does not go to the renal vein at all. Let's write. Its renal vein concentration, renal venous concentration of X is 0. It does not go to the renal vein at all. Once it comes into the renal artery, in the renal blood flow, then it is completely excreted into the urine, 100%, all of it. Which means its urinary excretion rate itself can give us the renal blood flow, amount of blood flowing through the kidney per unit time. So that's another, in fact, this is the most important property. Let me just explain this property again. Once a substance, this particular X, comes into the renal blood, then it is completely excreted into the urine. So its urinary excretion rate can give us the renal blood flow rate, isn't it? And therefore this is the most important criteria, that it does not go to the renal vein at all. By that I mean it excreted completely into the urine once it comes into the kidney. Okay, so let me just add one more point here. How is it that this is completely excreted into the urine in a single pass? Once it has come into the kidney, all of it comes into the urine. How is that possible? How does that happen? Look, filtration fraction is 20%. So any substance that is being filtered at the glomerulus, only 20% fraction is filtered. That means this X, 80% of its fraction must come from tubular secretion. So 20% by glomerular filtration and 80% by tubular secretion, 100% coming into the urine. Okay, that's how the X behaves, that once it comes into the kidney, all of it comes into the urine. In that case, renal venous concentration of X, see now we don't have to access renal vein to collect the sample, because we already are aware that this substance does not go to the renal vein at all. Its renal venous concentration is 0. We don't have to bother ourselves with renal venous concentration of the substance. So renal vein concentration of that substance is 0. Watch it. Watch it now. What was the clearance equation? The clearance equation is UV upon P. Here. And we started out with Fick's principle for measurement of the renal blood flow or renal plasma flow, and we have certain criteria, certain properties of that particular substance. If those properties are there, then Fick's equation became the clearance equation of that substance. See? So it means now Fick's equation becoming the clearance equation of that substance means that substance clearance, the clearance of that substance will give us the renal plasma flow. And all these properties, all three properties are there in the para-aminohippuric acid, and therefore para-aminohippuric acid PAH is most convenient to use to measure the renal plasma flow and renal blood flow. PAH clearance will be equal to renal plasma flow. I am using the terms interchangeably because PAH will be injected into the renal plasma and it will be the filtration and secretion from the plasma. So it will give us the renal plasma flow. Okay, and the clearance equation is U into V upon P. Clearance of PAH is same as, or it will give us the renal plasma flow. And that's the basis for using PAH, para-aminohippuric acid, to measure the renal plasma flow. But to me, the most important criteria is the third one. And I would repeat it third time. Once the substance comes in the renal blood, in the kidney, in the renal artery, then all of it comes into the urine in that single pass. None of it, no amount goes into the renal vein. So its urinary excretion rate can give you the renal blood flow rate. That's the simple way of putting this particular explanation. All right. So renal plasma flow being measured by injecting the PAH. So it becomes very simple now. As I said at the start, that very simply we just have to measure the plasma concentration of PAH, and then we have to measure the total excretion rate of PAH into the urine, and that's it. It will tell us the story. It will tell us about the renal plasma flow. All right. Finally, renal blood flow can be derived or calculated from renal plasma flow. How? Simple. What is the difference between blood and plasma? Whole blood and plasma. The difference is that of hematocrit, isn't it? Any unit quantity of blood, 45% volume is of hematocrit or cells and 55% volume is of plasma. So the difference between whole blood and the plasma is of hematocrit, and therefore renal blood flow is equal to renal plasma flow into 1 upon 1 minus hematocrit, or 100 upon 100 minus hematocrit. If we are taking the volume of whole blood as 100, then 45% will be cells and 55% will be plasma. Or if we are taking the volume as 1, then 0.45 will be cells and 0.55 will be plasma, whichever way you take it. So that finally will give us the renal blood flow, and that's the basis for using PAH to measure the renal plasma flow the most convenient substance for this particular purpose.